Okay, what happened was with underestimate and overestimate of distance travel is exactly the procedure or the process that we have done with left hand or the right hand sum for the area under the curve. Again, remember one thing, distance travel was equal to velocity times time, and that's why distance will be area under the curve, which we tried it in class in different ways. Some of us use trapezoids, some of us use rectangulars, some of us use rectangulars perpendicular to y-axis, perpendicular to x-axis. So what we're saying here, actually the best method for us to be able to calculate the area under the curve or distance travel is performing rectangulars perpendicular to x-axis with equal slices, and each slice will be delta t. So it doesn't matter that delta t is 2 or 1. What matters is where do we start to draw the first rectangular line. So on this one, the left hand sum one, hence one thing, we're starting from t0 and we draw a rectangular. We keep going like that, and the last rectangular I will draw will be at Tn minus 1, and I am starting from t0, and we are in the interval from time a to b. And that point on the graph is referring to f of Tn minus 1. And we are starting from f of 0. So for left hand sum, our interval is from a to b. Delta t's are equal, but then we are starting from t equals 0 to t equals Tn minus 1. And what do we obtain as a sum? That's what we need to write it down here. Total distance traveled or area under curve with this approximation will be f of t0 times delta t, because each of these intervals are delta t measurement. Each of them are delta t, plus f of t1 times delta t. I'm not going to bore you to that. I'm just going to write down the last term. The last term will be equal to f of Tn minus 1 times delta t. Then we can write down our big term in the summation formula by saying that sum I is going from somewhere to somewhere. That's what we're going to be doing. F of t times delta t. So here we're going from I equals 0 to Tn minus 1 f of ti, and that is going to give us the left hand sum. So this is one thing you need to remember with the approximation. But what happens with that left hand sum, we're omitting that little areas here. We're not taking that into consideration. So there might be an alternative way for that. and that is called right-hand sum. So the difference in left and the right-hand sum is we are starting to draw our rectangles from first the right-hand side. First the right-hand side and the first right-hand side. Everything else is the same. So instead of starting from T0, we're actually starting from T1 and we are going till Tn. So again the interval from A to B, but this time we are starting from T1 and we're going to T sub n. So how is it going to affect our sum? Then in this case, total distance traveled which is again area under the curve, be equal to f of t sub 1 times delta t, f of t sub 2 times delta t, plus f of t sub n times delta t. Then our right-hand sum will be equal to I f of ti delta t. We are going from I equals 1 to I equals n. Alright. So why is that important for us? Because we want to know how much we travel by knowing the velocity. And hence one thing, velocity was the derivative of the position. So it will be better actually to put dx over dt for those axes. Dx over dt for those axes, thinking that x is a position function. If we take the derivative of position with respect to time, we will obtain the velocity function. So what we're saying here now, if we slice those intervals here, delta t's are b minus a over n. So how much of n I do want to have here, I just subtract the last term minus the first term and divide it by n, and that will give me the amount or size of my slice. As we have seen on previous examples, smaller the delta t, better the approximation. Now we're thinking that if we take those delta t's so small, then we can make a best approximation for area under the curve, and that is going to bring us to definite integral. So how do we do that? Let's see how are we going to bring it to integral. So if I take limit as n goes to infinity, sigma I equals 0 to n minus 1 f of ti times delta t, which means that slices or delta t's are so small in the left-hand sum, hence left-hand sum because it's going from 0 to n minus 1. Or another way of saying it, limit as n goes to infinity, sigma, this time I goes to 1 to n, again f of ti times delta t, which is slices of delta t's are so small that I am actually finding an integral or area under the curve. So this is how we write it down. Integral is from a to b f of t dt will be equal to limit as n goes to infinity, left hand sum, which will be limit as n goes to infinity, sigma I equals 0 to n minus 1 f of ti delta t. Or same way again, integral from a to b of a function with its derivative, limit as n goes to infinity, right hand sum, which will be limit n goes to infinity, sigma I equals this time 1 to n f of t sub I delta t. Each of these integrals, called Riemann sum, f is called the integrand. This is Riemann sum. It's called integrand. I and b called limits of integration. The reason we have that S-looking shape for the integral, this is an old-fashioned S, which stands for sum, which stands for those sum. That dt is coming from delta t, from the factor of delta t. The limits on the sum for 0 to n minus 1 or 1 to n on the right hand sum, whereas we have the limits from a to b. Okay, that's it for me. I hope it will be helpful. I'll see you on Monday. I will be posting the homework that you need to submit it to me today. If you have any questions, let me know.